First thing I want to bring up, mention, remind, let you know about, we are in week 12. Uh, 2 weeks from now, week 14, I am going to be in Washington, D.C., attending the NSPS student competition. I will not be here at school whatsoever Monday or Wednesday, the days you guys are really concerned with. Therefore, we will not have any lectures on Monday or any labs. I hate to disappoint you. Sorry about that. Let me kind of rephrase that. We will not have any structured schedule lab time. However, the lab we are going to start next week is a bit time consuming. So I'm not going to give any lecture or scheduled lab time. However, I'm going to want you to continue working on the lab during week 14. I had in the syllabus here possible substitute instructor to be determined. I'm going to say it's been determined there will not be a substitute instructor, so you do not have to come here for my class. But I want you to work on that lab. I probably will remind everybody again next week in week 13. Okay, so this week what I want to talk about is chapter 17 in the elementary surveying book. It is mapping surveys. Please read the chapter. This is just kind of a summary review of the chapter, not meant to substitute for reading. Talk about mapping surveys today. So hopefully the learning objectives we get done is define what mapping surveys are, differentiate map types, understand scale and accuracy, explain contours and terrain representation, describe mapping methods and technologies. I know. Well, I'm excited too. Love it. What's a mapping survey? Well, that's a great question. I'm glad you asked. Thank you for bringing that up. So what we got going on here, mapping surveys are made to determine the locations of natural and cultural features on the Earth's surface and to define the configuration of that surface. That's the textbook definition there. Natural features are listed here, not all inclusive. There are many other things. Natural features include vegetation, rivers, lakes, oceans. Vegetation, that could be tree lines, outline of a woods. If you're out on out in farms doing surveys, could be a differentiating between a plowed field and the yard. Vegetation, things like that. Rivers, creeks, streams, ditches, essentially anything that would be related to drainage in some way or another. Cultural features, also called artificial features, are essentially anything that is man-made. So we're talking roads, railroads, bridges, buildings, boundary lines, and things along that nature. When we talk about the relief, we're talking about the elevation, the lay of the land. Think of like rolling hills, mountains, valleys, things of that nature. So hills, valleys, plains, and other surface irregularities. We produce these types of maps for analysis and design. Types of maps we have planimetric and topographic. So just to try to spice it up a little bit here, I try to add a couple pictures. Hopefully they're viewable and visible for you in the back. The planimetric would be the image on the left. That is depicting natural and cultural features in a flat plan view only. So we're looking at like an XY or a northern easting, flat line work. Topographic maps also depict natural and cultural features. In addition, they show configuration of the Earth's surface. So they show elevation, they show that relief. Might be a little difficult to see on that um, image on the right, but there are contours on that depicting elevation. Uh, Again, that's also of Cincinnati State, and I think everybody who has been here on campus knows that the campus sits on top of a hill. There's quite a few contours in that picture. So planimetric, flat, plan, topographic 3D, or 2D representation of the 3D surface, I guess would be a good way to say it as well. Some applications of mapping include engineering design, construction planning, GIS, environmental analysis, resource management. So surveyors will go out onto typically like an undeveloped piece of ground, create a topographic map locating the existing ground features, focusing on drainage type features, any existing utilities or man-made features that might be around there. Develop this topographic map, and engineers will look at that and then start designing, okay, where are we going to put the roads? Where are we going to put the utilities? Where are we going to put the buildings, houses, whatever? And also with like construction planning, once the engineer has developed a set of plans, there's also usually some earth moving going on, cut, fill. So for construction planning, they will look at those plans and say, okay, how much dirt do we have to move? How much cut do we have to either make? How much fill do we have to make? Where's that cut going? Where's that fill coming from? Do we have enough? Planning in that instance. So engineering, design, construction planning can kind of go hand in hand at times. GIS, the Geographical Information System, right? That's what that stands for. I've been having a couple brain farts lately, and my head just kind of locks up all of a sudden in mid-speech. I guess the best way I like to describe the GIS, those images I showed on the last slide, I pulled that off a Hamilton County GIS website. Way back when a surveyor would go to do some boundary surveying, boundary work, we would go down to the county administrative office, the courthouse, whatever. And in the tax map department, they used to have these enormous books, huge. They were like literally 3 feet by 3 feet, 4 feet, I don't know. Either way, they showed parcels, all the land within the county. They are very adamant about in those tax maps that this is to show an approximation of the size and shape of the parcels. We call them tax maps because it was for taxation. We want to know approximately the size and shape. GIS is pretty much still the same thing. They go in, the auditor's office, the engineer's office, whoever's in charge of the GIS, and they take all these parcels and they put them together. Now, in the real world, everything doesn't line up perfectly and match perfectly because if you think about it, we're dealing with a curved surface and we're looking at plans that are on a flat plane. So they do what I like to call rubber sheeting, where they kind of, translate, rotate, scale some things to make every line match perfectly. That's not the true case, so to speak. And that's a bit of a frustrating part that surveyors deal with is the general public doesn't realize that it's an approximation. I mean, it's generally close and it's generally in the right area, but it's not correct and accurate. So you get a lot of homeowners occasionally start arguing with the surveyor that they're wrong because the GIS says my line's over here. Well, the GIS isn't not correct. We're actually going out there, surveyors, measuring evidence, measuring monumentation, and determining where that parcel is, correct size and shape. A little surveying joke we like to say is GIS stands for Get It Surveyed. But GIS is very useful, and it does has its usefulness. We use it regularly, daily. GIS also has a lot of information on it. Like I was showing on that other slide, the topographic map, those contours were from GIS. How accurate are they? Not exactly sure. I would strongly recommend getting some precise survey work done to verify. Environmental analysis. There have been times where I myself actually have gone out on job sites to do a topographic map where the environmental analysis is the concern. Locating areas that might have been delineated by an environmentalist as wetlands. For development, you have to worry about wetlands, the EPA, things of that nature, like what you can and cannot disturb, or if you are disturbing wetlands, how are you going to replace that? So I've mucked around through some swamps and up and down in the creeks and streams doing things like this. Another thing, I don't know, is kind of cool. I actually was in the woods locating specific trees, and I had an environmental person with me who was like one of 3 or 4 people in the whole entire state that was licensed for, I don't remember exactly, but it had to do with bats. And he was locating trees that were habitats for a specific type of bat. And then I was locating them on a survey. In just my own goofy way, I was sitting there thinking, okay, this guy's a certified bat guy by the state. I'm working with Batman today. How cool is that? Not really, but made me chuckle, and that's all I care about. Resource management also can kind of go along with your GIS. There are various layers within the GIS where you can, in some instances, look up, say, an inventory of utilities. For example, how many fire hydrants are in this particular area? Or catch basins. How many types of storm sewer catch basins are there in this particular area? Where do they go? Some of it will even get as detailed as like tell you the pipe diameter, the pipe material, maybe when it was installed. But that's a good resource management in the case of like a utility, especially if they have like an install date on there. They can also review that and say, okay, this is getting to the end of its designed lifespan. Might need to keep an eye on this area for future repairs and or replacement. The environmental analysis can also be put into a GIS database, your resource management in a GIS database. Some preliminary design and some preliminary planning can be done off of GIS. These all are basically kind of intertwined. Not just one specific thing. They all kind of work together. And that's what mapping, or a couple applications of mapping. I think I got this as an extra slide, or I got an extra slide in the back. Talk about this a little bit more in depth later on. Some methods of mapping. We have some aerial methods and ground methods. The aerial methods would be using like drones or manned airplanes, doing photogrammetry and LiDAR. LiDAR being the light detection and ranging. It's where we see all these point clouds nowadays. Photogrammetry, you can take a series of photos, and with the proper amount of gap and overlap in these photos and having control points in these photos, you can actually take 2D pictures and turn them into a 3D map. Ground methods, we would have like the conventional total station, GNSS receivers, as well as terrestrial-based LiDAR. The LiDAR, a lot of people will even just kind of refer to them as scanners. We got a SLAM scanner, which is one that you can carry and physically walk around and collect point cloud data as you are moving in real time. Usually, these two methods are combined. Typically, the way that would be combined would be starting off with ground methods, establishing control. Um, if you are going to use aerial methods in this process, you need to have control points that are visible in order to properly georeference the imagery or the LiDAR data, properly have it georeferenced correctly where it is in the world, the proper orientation, as well as setting it to the correct elevation. Likewise, some other ground methods would be shooting some random or intermediate points around. Photo identifiable points is a common name used, where the photogrammetry and the LiDAR can use those for ground truthing, meaning they can kind of just a check shot where they're verifying how close, how good is the LiDAR data compared to the ground data. It's kind of a check for accuracy. Ground surveys still matter because that is going to be the main way of establishing control. Like I was talking about a little bit earlier, the photo identifiable points, some random check shots to verify aerial accuracy and to help improve accuracy. A lot of people kind of seem to think sometimes that drones are going to replace the surveyors. They're not. They need to be looked at as a tool for surveyors. Way back when, even when I first started out when I was your age surveying, the total station was the tool all surveyors hadn't used. As the GNSS receivers came along, got more commonplace, surveyors started implementing that more often. And sometimes I kind of feel like I've seen various folks kind of take that GNSS receiver as this is it, this is the only thing I need, and not even look at their total station anymore. The drone's not going to replace the surveyor, it's a tool. Like the GNSS receivers, like your total station, it all depends on what kind of job you're working on, what you're doing, use the proper tool. Like you need to drive a nail into the wall, you're not going to grab a screwdriver, right? You're going to grab a hammer. You need the right tool for the job. Screwdriver might work, might not. Definitely be the hard way around, but get the right tool for the job, get a hammer for a nail. I wanted to include this bottom portion here. I pulled this straight from the Ohio Administrative Code. So this is a law in Ohio. There is the Ohio Administrative Code, and then there's like the Ohio Revised Code. One is actually statute law. The other is kind of more guidelines, maybe how to interpret the law a little bit, or just, I think the Revised Code is where all your like minimum standards are. Here's what you should be doing at a minimum practice. Either way, per Ohio Administrative Code, Chapter 4733-31-01, this is the way the state of Ohio defines surveying. Each state has their own statute and defines surveying essentially in a very similar way, just usually worded differently. And I feel like this kind of also gets a little wordy. But what it's saying is, surveying shall mean any professional service performed for the purpose of determining land areas, the monumenting of property boundaries, the platting and layout of lands and subdivisions thereof, including the topography, the alignment, and the preliminary grades of streets, the preparation of maps, record plats, field note records, and property descriptions representing such surveys. Catch my breath after that one. The adequate performance of such work involves the application of special knowledge of the principles of mathematics, the related physical and applied sciences, and the relevant requirement of laws for adequate evidence to the act of measuring and locating lines, angles, elevations, natural and man made features in the air, on the surface of the earth, within underground workings, and on the beds of bodies of water. I just kind of bring that up too because there's been a lot of stuff lately and over the last few years with the use of drones and how those have been coming into play. Well, I hear a lot of people, they want to get a drone and start a side business. Well, that's fine, long as you are careful with what you are doing. For example, if you want to hook up with a realtor, fly a drone to take some aerial photos of property, great. Not a problem, cool, have at it. There have been companies that will take just the GIS line, put it overlay it on that aerial photograph. The state and various people will interpret that as, okay, you're defining property lines, you are surveying without a license, you can get in trouble. I mean, this is legit law. A lot of times the Board of Engineers and Surveyors will try to just reprimand you with hopefully a cease and desist letter, maybe a small fine. However, if it proceeds or gets worse, they can take legal action, get the state attorney general involved. And that should be pretty much similar, common with every other state in the area. So where it might sound like, oh, I'm just taking photos that could be used for photogrammetry, if you're starting to produce things like that, you're kind of sort of, at least in Ohio, could be interpreted as practicing land surveying without a license. I think it's kind of important. That's why I included this little snippet of law into this as far as all this stuff. Map scale. So we have three types of scales we use. Ratios, the book calls it equivalence, like engineering scales, and graphic scales. So the ratio represents a fraction. And an example, you could see this, especially if you look at like a USGS quad map. You can see down on the bottom 1 in 1,200, 1 in 24,000, something like that, some numbers. The same units are used for the map distance and the corresponding object distance. So whatever you scale on the map, however many inches, feet, centimeters, whatever, would equal the same inches or meters or feet, whatever, on the actual ground. So for example, here, like the scale of 1 in 1,200 could mean 1 inch on the map is equivalent to 1,200 inches on the ground. Pretty simple. Nothing too crazy. Any questions? This is the preferred method for geographers and and they also utilize the graphic scale. The engineer or equivalence type scale is what we have seen, what we're used to, what we use, like 1 inch equals 100 feet, for example. We have the engineer scale. We did that drafting plat lab earlier in the semester. We used the scale to scale out our distances, measure our distances. So we have things like 1 inch equals 10 feet, 1 inch equals 20 feet, so on and so forth. This is the preferred method of engineers and surveyors, along with utilizing a graphic scale. The graphic scale, that's something else we also included on our survey plat, right? We had that little bar and ticked off our distances. A bar scale, graphic scale, whatever you want to call it. The intent of that is you have a drawing that was produced on some size sheet of paper. If it's recorded in the county and you go and download it, print it out. Chances are you're not going to print it out at the same size sheet of paper. Probably going to do an 8.5 by 11, 11 by 14, 11 by 17, whatever. Legal size is 8.5 by 14. Your scale's obviously going to be a lot different. You have the scale bar there, so you can actually measure with a scale or a ruler or whatever and apply a scale factor to still use and scale on that drawing if you'd like. I just thought that was kind of weird. So every county in Ohio and probably about every other county in every other state has different requirements for when you do submit and record survey plats. Some counties might want you to do a plat on a 24 by 36 sheet of paper, 18 by 24, 11 by 17. I don't know. I'm just throwing random numbers out. And that's all fine that they require your survey to be on a specific plat. However, like I was saying, when you go, the next surveyor comes and gets a copy of that plat, they're not getting it at the same size that the county requires. So your scale is going to be different. I believe in Kentucky, I could be wrong on this, but I believe like most counties in Kentucky require surveys to be done on either like an 8.5 by 11 or an 8.5 by 14 sheet of paper. Does that sound right? Have you ever come across that? I think that is. I feel like I've heard a lot of Kentucky surveyors talk of that, and I believe what the intent is to have your survey required on that size sheet of paper. They can associate it, put it with the deed of that property. So, like if you are doing some research on a boundary, you go pull a deed. If there was a survey done on that property, it should be there with the deed. I think it's a great idea. Unfortunately, in Ohio and Indiana, if you want to do something like that, you pull the deed. The deed might reference a survey. The deed might not reference a survey. You got to go to the engineer's office to see, is there a survey on that property? Some counties don't even require you to record a survey, which to me sounds like a wild idea too. I think if you're going to do a survey on a property, it should be recorded. But what do I know? I feel like I got a little off tangent on that one there. Scale, ratio, engineering, graphic. Questions? So we talk about two types of control required for mapping. This is before the data collection itself happens. We have to have horizontal and vertical control. Horizontal being the position, the northing, easting, the XY, however you want to look at it. And that can be created from total stations, GNSS, and triangulation. I believe that was the three that were listed in the book. I have not ever done any triangulation in my life. Now, when back in the 1920s, 19 teens maybe, the government started surveying across the country, literally across the country, up, down, east, north, south, east, west. And they did this by triangulating. Essentially, you need a distance on a baseline. You set up on that baseline, you turn an angle to some point. You move to the other end of that baseline, backside that other end of that baseline, turn an angle to that same point you referenced from the other one. You have the interior angles, it's a triangle, you can start calculating distances around. Then you'd move to another station, backside that initial baseline point, and then that new one, turn out. Just kind of keep turning triangles and calculating as you go. Traversing we're familiar with. We did a horizontal distance or horizontal angles. GNSS we don't touch in this class, but that's determining positions by latitude and longitude using our geodetic datums, being an ellipsoid and a geoid. The vertical control. You have your differential leveling, trigonometric leveling, and GNSS using the ellipsoid and the geoid. A lot of times when surveyors go out and set control, the control points are both horizontal and vertical. However, that doesn't absolutely have to be the case. You can have separate individual control points that have only horizontal or vertical position associated with it. If you have a point that has only vertical control on it, we usually call that a benchmark. The differential leveling, we just did that out on the back hill. Good fun, right? Right? Best lab ever? Yeah? Yeah? Okay. We learned a bit from that. The trigonometric leveling is done when you're using a total station. So when you set up a total station, you're measuring the height of the instrument. You're measuring the height of your prism pole, your target. The instrument is then measuring a zenith or vertical angle and a slope distance between it and the prism. Knowing that zenith angle or vertical angle and the slope distance, it does the trig and calculates what's the horizontal and vertical distances of that triangle. Then can apply, okay, if you're set up on elevation, add your HI, your instrument height, shoot however far over, and subtract that vertical distance, and then subtract the rod height. You got your elevation of your next point. So a lot of times if you are doing traversing, you will do all of that at the same time. The GNSS, we use the ellipsoid and the geoid. That's our geodetic datum. Now, I say GNSS, and I try to be very specific in saying that. Does anybody know what that means, what that stands for? Anybody? There you go, Global Navigation Satellite System. We typically here say kind of generically GPS, Global Positioning System. What GPS is specifically is the United States constellation of satellites up in space. There's others. Russia has some, China, Europe. All of these satellites together make up the GNSS. I kind of think, I don't know, do people still say or use Kleenex? Yeah. Kleenex is a specific brand of facial tissues. Technically, they're all facial tissues. It's just, you might say, give me a Kleenex, when really there's a box of puffs or whatever there. Yeah, that's kind of what I mean with like the GPS, GNSS. Does that kind of make sense? So with that, we have our horizontal and vertical datum, the ellipsoid and the geoid. The ellipsoid is a mathematical model representing the shape of the Earth. That's where our latitudes and longitudes are derived from. As well, your GNSS receivers are measuring from the ground to the ellipsoid, an ellipsoid height. That's what it does. The geoid is a rough model, undulating is a fancy word, I guess. Think of that as sea level, approximately, roughly. The geoid at times can be above or below the ellipsoid. When we know from the ellipsoid height and it's the Latin long, the software knows where the geoid is in reference to where we're standing and where that position is, and measures the distance from the geoid to the ellipsoid. When we do the math of the ellipsoidal height and the geoid height, that gives us an orthometric height, is also kind of what we refer to and call elevation. Pretty exciting, isn't it? And the good news is, you folks as surveyors are going to see new geodetic datums in your lifetime, hopefully maybe coming out this year, maybe next. We'll talk about that more in another class. I don't know, sometimes I feel like I kind of get a little too detailed and wordy and kind of go down a slight rabbit hole, shallow rabbit hole. Anybody have any questions about the traversing, like the horizontal angles that we did? Um, differential leveling, things like that? Comments, concerns? So we'll start talking about contours. Those are what are on topographic map. That's kind of what differentiates a planimetric map from a topographic map for showing elevation. A contour line is a line connecting points of equal elevation. Does that make sense? So you pick some elevation and you would map out where each one of those elevation points fall, and all those points would make a contour line. We haven't also talked about the contour interval. That is the constant vertical distance between two consecutive contours. So a lot of times you will hear regarding a topo map, those are 1 foot contours, 2 foot contours, 10-foot contours, something like that. That is referencing the contour interval, meaning the vertical distance between each contour line. That's always going to stay the same. Two contours aren't going to be 1 foot apart, and then the next one will be 5 feet apart, and then the next one will be 3 feet apart. It's the contour interval is constant and stays the same. The book talks about the horizontal equivalent, which is the horizontal distance between any two adjacent contours. That can vary. That changes. Sometimes it's the contours are very far apart horizontally. Sometimes they're close together. Contour interval is constant while the horizontal is variable. The horizontal also kind of tells you about the slope of the ground. Everybody good on those definitions? Locked into memory? So we talked a little bit about contour characteristics. Contours only close on themselves. They do not cross or merge, except in the case of an overhanging or vertical cliff or vertical face wall. They are perpendicular to slope. The horizontal spacing indicates the slope. Horizontal equivalence, whatever I called it on the last slide. So your flat ground is indicated where contours are spread apart, widely spread apart. That's representing a very flat slope. The closer horizontally that contours are, indicates the steepness of that slope. So if you see contours really close to each other, that's steep. Far apart, getting flatter. If the contours horizontally are a uniform distance apart, that's indicating a steady, constant grade, steady, constant slope. Make sense? I don't think here you probably will ever run into any overhanging cliffs. Now, if you go out west, then yeah, you probably will. We don't really have a lot of vertical cliffs here. However, we will see on plans things like retaining walls, or if you look at point clouds and generate a surface from a point cloud, now you got building walls. They're pretty vertical. It looks like everything's going to run right into each other. Some other contour characteristics here. If you have a series of closed contour lines, that represents a hill if the higher values are on the inside. So we're looking at elevation 60, 65, 70, all the way up to 80. Your 60 is the furthest out. As those circles move in, and the numbers are getting higher, that means you have a hill. Likewise, a series of closed contours can indicate a depression if the higher values are on the outside. Pretty clear? Makes sense? You will see if you look at a set of construction plans for like a subdivision or something like that, depressions, the engineers will call them either detention or retention basins. Pretty common. Pretty much common in any development. You see detention or retention basins. Probably more so detention basins. Pop quiz. Does anybody know the difference between a detention basin and a retention basin? Anybody? Anybody? Anyone take a guess? Yes. A retention basin, correct, always has water in it. It's always retaining water. A detention basin, think of like back when you were a kid in grade school. You got in trouble, you got detention. Everybody was released, you were held back and then released out later. So detention basins, okay, maybe, am I the only one that had detention as a kid? Probably. Okay, I can be, that's fine. Detention basins will collect water during a storm, hold it, and release it out slowly. As it started to fill? No. No. I could potentially be scared depending on how quick that water comes in. Other contour characteristics talk about ridge lines and valley lines or ditch lines. Contours cross at ridges and valleys at right angles. If the higher value are inside the bend or the loop, it indicates a ridge. If the higher values are on the outside of the bend, it represents a valley. This is kind of a hard one really to wrap minds around. It still kind of trips me up. I still like literally would have to look at contour maps and kind of look at the numbers and get that in my head. When you're looking at valleys or ditches or creeks, they kind of form a V and the V points upstream. So I guess one thing I do kind of want to point out here, a lot of times, not always, but a lot of times your ridge lines will look a lot more bowed, a lot bigger radius here. Where your creeks and things like that will usually have a sharper, little bit more pronounced V shape to it. And the V is pointing upstream, where the water's going, not where the water's coming from. Wow. What are you doing, Chris? So the water's actually flowing downstream this way, but the V itself is pointing upstream. I think what I want to do is try to find like maybe some isometric views of this and kind of have it tilted up. It might help kind of visualize this a little bit better as well, seeing the ridge and the valleys. Does that kind of make sense? Kind of help out a little bit? We'll nail these on the quiz or exam. Oh yeah. So there's a couple methods for contouring. We have the direct method in the book called Trace Contour Method, and we have the indirect method, which the book calls Controlling Point Method. The direct is rarely used. I honestly have never done it in my entire life. Never seen anybody do it in my entire life. Not saying it's not done, I've just never seen it or done it. But what you're doing is actually locating the elevation of whatever contour you're searching for, you'd mark that point, survey that point in, and then connect the dots, and that's where your contour lines are. I would say it's very time consuming and very tedious, therefore not used. The indirect method or controlling point method is what's more commonly used, what we do today as surveyors. It's considered to be way more convenient and faster by surveying control points. That are critical to the proper definition of topography. The controlling points, so yeah, did I hear somebody just ask that? Yeah, great question. Thanks for asking. Controlling points include the high points, low points on the terrain, as well as break line locations where ground slopes change. Okay, so you're kind of looking for the high point of ground, you're looking for the low points of ground, you're locating that. Break lines, locations where the ground slope changes. This is getting a little loud out there. I want to close the touch. But I didn't want to lose you, Ben. We'll talk a touch more about break lines as we proceed. Any questions on any of this stuff here? So looking at the indirect, this isn't quite the best graphic, but I like to try to break it up with pictures when I can. So again, indirect is convenient, faster. You're doing the control points, which properly define topography. When you are out in the field locating, doing this topo work, drainage is pretty much the main key factor. That's the one thing engineers want to know. Contractors that are building, they want to know where's the water flowing, which direction, where's it going. So we do high points, low points, and break lines where that changes. So this isn't quite the best example here, but this would be, you have some intermediate points and then some points along the center of a stream. That's kind of all I really want you to look at and pay attention to with this. I need to get a better graphic for that. Break lines. They define the terrain or changes in terrain edges. So for example, drainage in general. Again, that's the most important. Engineers want to know, where's the water going? Where's it flowing? The contractors, the construction workers building the sewers, where's that water supposed to be going? That's crucial. So we have break lines, things like top of banks, toes of slope, ditch lines, creeks, streams, rivers, things of that nature. We also have roads as break lines, bridges. This is not an all-encompassing list. This is just kind of a generalized. What I had here, okay, so this is another from the GIS with the GIS contours and part of the school here. Particularly over by the ATLC and the health building and the parking garage, this portion of the roadway. See how contours are kind of coming into the road, they change direction a touch, and then when they leave the road, they change direction again. That's a controlling feature of where a slope is changing. Even if you think like out on the back hill there where we did our horizontal angles and we did our differential leveling, where the A and D control points are kind of up on the top of the hill, it's not really flat, but considering that whole back hillside, that's kind of the flatter area, right? Then there's kind of a spot where the slope breaks and it starts getting steeper as you go down to B. And then when you get down towards C at the bottom of the hill, it starts flattening out again. Break lines, where the slope changes. Like so, up there by A and D, there's kind of a line-ish. You can kind of see like, okay, it's going flat so far, and then the hillside changes slope. These are break lines. Any questions on any of this? Roadways are critical. Again, it really does all tie into drainage. Where's the water flowing? Digital elevation models, DEMs, also known as digital terrain models, DTMs. You'll probably hear the term DTM a lot more often. Pretty interchangeable, pretty much mean the same thing. There's two basic geometric configurations that are normally used in the field for data collecting. There's the grid method, the irregular method, and typically when you're out there in the field doing topo, you're using a combination of both. The grid method, it kind of got a little bit of an example going here. Points spaced on a regular grid. So that's what these dashed gray lines are. Some distance, and whatever that interval is, you're getting a shot here, here, here. Whatever the interval distance is this way, you'd move down the same distance and continue another line. Go down, back and forth. The irregular method is pretty much like that controlling point where you're hitting your high points, your low points, your break lines. Very common. Say if you're out in the middle of a farm field that's getting ready to be developed, doing a topo, chances are there's probably some ditches running through that field. Those would be some controlling points that you want to highlight and define that ditch line. That would be a break line. Otherwise, if it's gently rolling and not a lot of real crazy elevation change or hard elevation change, you're probably going to just do a grid. It's not uncommon if you're going to go do a topo, the engineer or whoever's giving you the job will say, we need ground shots done in every 50 feet, 25 feet, whatever. So you basically will start walking. If I'm doing a 50-foot grid, I'm going to get a shot. I'm going to walk 50 feet and get another elevation shot, 50 feet, another elevation shot. Go however far I need to. Walk over 50 feet, get an elevation shot, and start working back that line every 50 feet, if that's the interval that they are looking for. Then likewise, if there are some high spots, low spots that need to be defined better, you need to pick that up. And break lines. Any questions on that? When I was out in the field, what I used to like to do, especially with like a brand new co-op student, if we were topoing maybe a smaller area or topoing an area, I'd kind of break off a small area for them to do on their own and tell them, look for your break lines, get your break lines first, and then kind of fill in the blanks where you think you need to kind of make up extra, get some extra ground shots so we have enough coverage. I would explain it a little bit more in detail, but that was kind of more or less the watered down thing is when you're starting off, focus on your break lines and then fill in the blanks. As you get more experience doing this, you'll do all of that all at the same time. But when I had like young college students out and teaching them about topo and things, get them kind of working on it and showing what we're doing, and then kind of turn them loose on a little area and say, okay, try this little area, focus on your break lines, fill in the blanks with ground shots in between. I think I kind of helped them a little bit. I'd never had anybody complain at me about it. Okay, here's that graphic again. This is a word you'll hear a lot, or an abbreviation you hear a lot, the TIN. It's a triangulated irregular network. For those of you that'll take Civil 3D, you will build surfaces in CAD. And this is what CAD is doing. It's utilizing the control point method with break lines points irregularly spaced. The points are connected to create a network of adjoining triangles. The commonly used standard to create these triangles is the most equilateral network. That would be ideal. However, they're not all going to be perfectly equilateral, and that's fine. They just try to look for like the triangles, what's going to be the most equilateral. Once you have this, okay, so here's your points. We'll look at this a little bit more. These dashed lines throughout here, connecting from point to point to point, making this triangulated network. That's your 10. What you do after you have your 10 established, all these points, you're going to find the contour lines. You're going to interpolate between the points along the triangle sides. So you're going to look at the elevation of this point. You're going to look at the elevation at this point and say, do I have any contours that fall in between there? We'll do the math and find out where do they fall exactly along that triangle line, and then start connecting the dots to make our triangles. That's what CAD's doing for you. It is way cool. We're going to do that. Our next lab that's going to take quite a bit of time is we're actually going to create a 10 by hand and interpolate contours and make a contour map by hand. Most fun, best lab ever since the last one. It's not difficult. The math is not difficult. We've calculated a few triangles here in this class. That's all we're doing. But I will say it is time consuming. So just be aware of that. The math isn't difficult, nice and easy. Just time consuming. So what we got going on over here, we're looking at the direct method of contouring. Figure A, which is over here on the left. Contours compiled by hand from controlling points A through N. Well, we know this wasn't done in CAD because you couldn't have points A through N. Okay, so B, the middle picture, is the 10 model, which is the dashed lines, are constructed from data of A, and the contour lines, which are the solid kind of reddish orangish lines, are derived from the 10 model. The stream is shown with the dotted line. Notice the difference in the way the contours look between A and B, especially your 10 and 20 contour. Pretty wild. There's something else I want to point out about that, but we'll look at picture C, which is the 10 model constructed with data from A, but with the addition of 2 points and the designation of lines EQ, Q, G, GP, PI as break lines. The contours shown with solid lines were derived from this 10 model. Something very important that I want to point out here with this. When you have break lines, your 10 will not cross that break line. The break line will always be an edge of one of your triangles, okay? So what I want to kind of point out to show you is here, so we got the stream in B meandering through. Looking at points H through M, that's going straight across what would be a break line. Bad. Do not do that. When you look over at the picture C on the right side there, you'll see all the triangles run to the break line. And one edge of those triangles are the break line. Okay? Interesting concept, fascinating. We're riveted. I know, I'm loving it too. I feel like I don't want this lecture to ever end. Anybody else feel like that? Oh yeah, I see a lot of heads bobbing up and down. That's right, Chris. We love it. Keep it going. Okay, so we kind of talked about this a little bit at the beginning. I realized as I went through this morning that it's repetitive, but in a little bit more detail. So the methods for collecting data with the conventional total stations. You're setting up your total station on a control point, backsighting a control point, establishing your reference line, your reference baseline, and you're generating coordinate points by measuring the angles and distances and elevations. The GNSS, again, Global Navigation Satellite System, is the all-encompassing uh, global positioning that we use. GPS, Global Positioning System, is again the United States specific constellation of satellites. I guess the big reason I also like to try to differentiate the two and say GNSS more than just GPS generically. We'll get into this in the control class, but when you're out there with your GPS receiver in the field and your data collector, I'm going to bet you a dollar you probably have a setting where you're telling your receivers, I want signals from every satellite constellation, from the United States, from Russia, from China, from Europe, from wherever. I want everybody's satellite signals coming at me and I want to collect them. That comes into play later on in the GPS control class. So with the GPS, you're using a couple different ways, the RTK and the RTN. Those are two methods of collecting. The RTK is real-time kinematic. You have a base set up on a known control point, and you have a rover going out on it, randomly, real-time picking up positions. Both your receiver and base are collecting satellite signals. The base is also shooting some corrections and information based on its known point and updating the position of the rover real-time. RTN, real-time network. Particularly in Ohio, most people would say using the VRS, virtual reference station. That's where you're just using a receiver only. You're connecting to a modem to the internet and you're receiving CORS information directly online. Personally, I know things have gotten better from when I was out in the field regularly using this, but when I was out there in the VRS, the Ohio VRS system was just kind of coming on and getting more and more popular. I'd set a couple points for control, then set up my total station and backsight. If I was within a 10th horizontal and 1500s vertical, I was like, okay, that's as good as it's going to get. I'm pretty sure it definitely is getting a lot tighter. It also kind of depends on your VRS where you are in relation to a core station. The closer your distance, the better results you're going to have. The longer your baseline away from a core station, it starts getting a little sketchy. I used to joke VRS stood for very reliable system, meaning that very sarcastically because I never had really good measurement results. But again, things have updated and changed a little bit since then. You're generating your coordinate points from datums and map projections. There's a difference between the two. Datums are the ellipsoid and geoid, which are giving us our latitude, longitude, and height. The map projection is, since we know the Earth is round, we're taking a sliver of that round shape and projecting it to a flat surface. Around here, you would know, oh yeah, I'm using my GPS, I'm in Ohio South, Kentucky North, Kentucky Single. Those are map projections. That's where we're getting our state plane coordinates from. Magic. Laser scanning, the LiDAR, they will give you very dense point clouds and very high detail. There's a lot of different manufacturers out there making scanners nowadays. And the amount of data that those collect instantly, like we're talking millions of points a second, you are getting an unbelievable amount of data. And some scanners are better for interior uses and some are better for exterior uses. Or I should say, some that are good for exterior uses aren't very good for interior. They could be used, these scanners can be used inside, say, like a warehouse, a hospital, a laboratory, where they need to map and model up all the pipes running through a room or an area. Very good to get a dense point cloud there. As a surveyor, I don't know if we actually need 1,000,000 points a second and just some ridiculous amount. I feel like that's kind of overkill. When I was out in the field, I had this instrument, a Trimble SX10. It was like one of the first combination total station scanners. And it was pretty good. It did well. But compared to other brands that would throw out 1,000,000 points a second, this thing was a dog. You know, it just couldn't keep up with stuff like that. But I would say those 1,000,000 points a second, those are like your Ferrari, your Lamborghinis. My little SX10, which isn't doing quite that, that's more like my F-150. That's my work truck. I don't need that much data for what I was doing. But it was good to have a lot. It still was a lot of data. The unmanned aerial systems, the UAS mapping. Again, we talked about the aerial imagery, photogrammetry. Awesome for large coverage areas. Construction sites will use the photogrammetry. Come out and fly a drone every week, every month, every something or other. And what they're doing is looking at progress and kind of also can measure, well, aside from progress, if there's like a lot of dirt being moved, they can start estimating quantities of how much dirt has been moved, how much dirt still needs to be moved, things of that nature. And geotechs would get mad at me for saying that. It's not dirt. Dirt's under your fingernails. It's soil. I've heard that a few times. Okay, whatever. It's dirt, man. It's dirt. I do put the unmanned aerial systems because the drones are increasingly popular and just exploding every day. There still is a use and being used today manned aerial aircraft with the camera payloads, with the LiDAR payloads in the belly of the airplane flying over. That's still used today, probably not nearly as much as before because of the drones. I don't know if anybody's ever looked at like the Ohio 3-depth LiDAR. You can actually download LiDAR point clouds of the whole entire state. That was all flown with a manned airplane and crew. Yeah? Trying to download something? Nice. Not nice. So yeah, I say unmanned because that is definitely more common, but manned aerial imagery is still used today. That's definitely going to be used more on the larger scale. I don't know how many people are familiar with this area here, like Hamilton County particularly, or the history of it, but over kind of on the west side ish, northern part of the county, where you get up near Butler County, there was a place called Fernald. There was an old, maybe uranium processing. I don't know. During the Cold War as a kid, I always heard that was a target for them to drop nukes on us. I don't know. Either way, Fernald has been cleaned up and is gone. I say cleaned up, maybe in air quotes. Uh, but I actually was out on that property one time, setting control for a manned aerial flight. And the reason I really remember this, I thought was hilarious. It's a nature preserve now. You're told how clean the ground is. For some reason, we still had to be escorted around the site. And it was so funny. It's like, tell us, yeah, If you were to take radiation samples here of the dirt, it's going to be cleaner than what's in your backyard. Don't go off the path. Jeez, well, Pete, really? I thought this was clean. Don't you dare go off the path. Boy, they were ready to like flog you if you thought of doing something like that. Oh, it's clean. It's perfectly fine. Don't go off the path. Oh no, it's the whole day on there. You can go. You can walk anywhere you want as long as it's down the path. I don't know. It was kind of a neat project still. Why is my lamp dimming? Come back, lamp. Okay, key takeaways. Scale controls accuracy. Control is critical. Contours represent terrain. Field methods must match project needs. So again, in the case of maybe you're inside a building, you're not going to be able to use your GPS unit. You're probably not going to be able to fly a drone. You have to get the instrument out. You're in a flat, wide open, 100,000 gajillion acre farm field. Yeah, get the GPS out, get the drone. It's going to be the quickest, easiest way to do it. Field methods must match the project needs. I was thinking about and talking earlier, as far as like that grid method goes for laying out a grid and getting elevations on a specific grid. I was thinking about this. It was probably close to 15 years ago. Me and another guy went to Kenwood Mall, and they were going to put in a Microsoft store, which is not there anymore, and I have no idea how long it actually lasted. But the store was completely gutted. We went in there and laid out like I forget, 2 foot, 5 foot grid, and and like literally painted the floor in this grid pattern, and then got elevations all the way through. So what they wanted to do was make sure the floor was level. They were going to build a false floor above that, because that's where all the electric and everything was going to run underneath the floor and then come up at the tables and stuff. It was kind of neat being there, but yeah, I don't think that store is very long lived. Hey, another instance like that too, actually down Central Parkway, as you get close to over the Rhine there, Sam Adams Brewery. They had in like one of the storage warehouse areas down there, um, the floor was kind of collapsing, caving, sinking in spots. And they're storing pallets and pallets and pallets of all their product. And they're running forklifts back and forth nonstop. So that's a problem when the floor was failing. We actually went in there on a Sunday, laid out a grid, and got elevations so they could determine, okay, what's where, how good is the floor, we need to get this fixed quickly. The reason we did that on like a Sunday was because they ran those forklifts were run 6 days a week. So because of the high volume of forklift traffic, it was like, you guys can only come in here on Sunday when there's no traffic going on. We're like, okay. It actually worked out pretty nice because just kind of the way that company was at the time. We didn't have the day off after Thanksgiving. So it was like, all right, we're going to work Sunday and we're just going to take that Friday off after Thanksgiving. And they were like, cool. So it kind of worked out, you know. Very rare situation to work on Sunday, but it might happen every great once in a while. That's another good example of the grid pattern, you know, in a sense, where the job needed a specific way of collecting data in a specific data set, along with what kind of equipment are you going to use in whatever environment. What does the project need? Inside factory floors, the grid works perfectly. Any questions on anything? Comments, concerns? Well, that's about all I really have for this lecture.